ओके, शुरू से शुरू करते हैं तो so today we are going to learn about the signal processing in a MATLAB, and the course name is Signal Processing on RAM. You can easily access to this code on a MATwork self-paced course website. It is completely free. You can get even a certificate and progress report by completing this course. So let's start. First of all, you need to know about the signals, that what are signals and what are the different types of signals. Although if you don't have any idea about the signals, then also you can start this course, because MATLAB gives you the easiest on-ramp courses where you can understand from the scratch about a topic. Okay, so let's start this course.
Hello, and welcome to Signal Processing On-Ramp. We live in a world of signals. Think of all the signals used just in your car. To play music, you can use the FM or AM signals picked up by your radio, or the Bluetooth signal from your phone. Your GPS uses satellite signals to pinpoint your location. And throughout your car, sensors generate signals to tell it when it's time to turn on your headlights, light a symbol on your dashboard, or deploy an airbag to save your life. In order for each of these signals,
So basically, signal is nothing but a variation of voltage at a distinct time, or you can say at different time. So based on different types of signals like analog, discrete, or digital signal, this time period gets changed. Like for analog signal, every voltage of a sensor means if a sensor is giving X signal, then in that signal at each period of time there is a different voltage, and this is continuous. That's why it is known as analog signal. So you can find a continuous, a discrete signal in an analog signal. What is continuous? Continuous give a continuous value of your voltage, or you can say functions at different time period, and in discrete it's give the value of your function at a instant time period. Okay, and the DC signals is totally different because it is introduced in our world because it solved the problem of error, and it also increased the accuracy if the levels of DC signals get increases. So we will talk about that later. If this course cover that, then it is good, but if it not, then I will tell you what is the difference between analog and AC signal. Okay.
to accomplish its task, it needs to be processed. At a high level, signal processing is a set of techniques which pre-process, analyze, and extract information from signals. In this course, you'll use MATLAB and Signal Processing Toolbox to compare vibration signals from 3 seismic stations in Alaska.
So basically, what is processing? Processing is nothing but to get the data from the signal that we are getting, and by the data I mean it can be anything, like we need data for Excel, or you can say we need the data to convert it into the different type of signal for our actuators and etc. So here what we have to do, we have to study about the pattern of the signal, like where the signal's amplitude is low, where the signal's amplitude is high, or based on that we need to understand about the situation at where the amplitude is low or high, and from that we can get the data, and we will use that data to make a new signal, or we can use that data to study the signal.
You'll identify the signal from an earthquake on the other side of the Earth and separate it from local earthquakes near the seismic station. You don't need to learn a lot of theory to start signal processing, but it will help if you know a little bit of MATLAB, just the basics. If you've never used MATLAB,
Yes, so you have to do both the courses, MATLAB and Simulink on RAM, to know about the signal processing, because if you don't know about the software, then you cannot able to adjust yourself within a signal processing on-ramp course in a MATLAB.
Before, it's easy to get started, and we recommend you first take MATLAB On-Ramp to get you up to speed quickly. Enjoy the course!
Okay, so let's start. So what does it says that generate signal when working with real-time data like seismic signals, sorry, you might know that expected result at each step of the workflow. However, you can check if your algorithm works by creating a known signal and verifying that the algorithm has the expected result. For example, how can you know that you have a correct calculated the power spectrum of a meshy earthquake signal? First, try your algorithm on a sine wave. Okay, what we have to do here? Our first task is to generate a signal. You must first choose the sample times for each point of the signal. Means we need to decide or select the sample times for our signal. Like if I have to choose a signal from 1 to 10, then my sample time will be 10, because 1, 2, 3 up to 10 is 10. So that is a sample time. I have to also write this because it is very necessary when you learn about the new stuffs in MATLAB. You have to make a notes, so it will be very easy for you. So is there any paper? Yes, there is. So let's start. Okay, to generate a signal, you must find the signal processing. Okay, to generate a signal, you must first choose the sample time for each point of a signal. You can choose the sample time by specifying these attributes: sample rates, that is fs in a hertz, sample time in a second, and end time in a b. Okay, generate a signal, first we need to select sample time for each point of signal. So sample rate is denoted by fs in hertz. Start time is denoted by a in seconds, and end time is denoted by b, and it is also in a second. Now what we have to do, you can create time steps for a to b with the colon operator. So if the start time is a and I need 1 by fs sample rates, and the end time will be b. So what we have to do here is we need to generate a signal, which is our task. Task is specify a sample rate of 100 hertz in a variable name fs. Okay, so fs equals to 100 hertz. 100 hertz. Okay, now then create a signal named t equals to signal that extends from 0 second to 1 second. So that extends from 0 second to 1 second with the sample rate of 1 by fs. Okay, so this is not perfect. We need to use this. Yep, now it is right. Let's see is our signal is created or not. So this is our signal which is created. You can see it's it has the value from 1 to 101. Why 101? Because we mentioned the end time and we mentioned the start time. So the gap is of 99, but the signal start from 0, so that also include the sample rates. That's why the total number of sample rate will be obviously plus 1 of your original sample rate that you have mentioned in your code. So you can see there are different types of signals, which is nice. Now what we have to do, we have to click on next. I also have to update my sheet that if I have to create a signal, now what we have to do, we need to create a, okay, first we have to write it. If I have to create a signal data, then for example, to create a signal data from 0 to 1 with 100 sample rate, we can use t equals to 0 colon 1 by fs 1. Oof, I'm not really feeling very well, that's why the disturbance is there. Now what we have to do, you can make a sine wave by using the sine function. You can see here, this is a sine function, that is s equals to sine 2 into pi f into t. Now we have the t, because t is nothing but a time period. F is the signal's frequency and the t is the vector of time steps. Yes, create a 5 Hz sine signal named sig. Okay, so this is a sig signal that we have to add here. Now we will copy this code, because the matlab is a case, oh, what did I did, sorry, matlab is a case sensitive language. That's why you need to copy paste everything, because if you write a code and you didn't mention the variable as a capital or a lowercase, then it will give you the error. Now we have to create a 5 hertz. The 5 hertz is nothing but the frequency of a signal. So this is a 5 hertz frequency of a signal, and now we have to create the plot, because without plot you don't get any signal data virtually visible. And by virtually I get, I sorry, not virtually, graphically visual. Now what we have to do, we have to plot sig versus t. Now we will click on submit and let's see is there any error or not. I don't think there has to be any. Okay, so the values are different. It's t versus sig. That's perfect. So now we get the signal that we have created. Okay, now the next thing we have to do is, first I have to write that steps in my sheet, so it will be very useful for the future task. Now if we need a sine, okay, wave this, then use s equals to sine 2 into pi into frequency of signal into t, that is interval time period, and t equals to 0.1 into f4, and then we have to plot t versus s. So we will get the signals in a graph format. Okay, now the next thing we have to do is, you can, I think I already done this part. Next task. Adding a noise to generate a signal is common because noise makes the signal more realistic. When your signal are more realistic, sorry, when the signal are more realistic, you can test if your signal processing techniques are robust to noisy data. So what is noise? Noise is nothing but unexpected voltage that comes when the sensor processes the data and give the signal. So it is unwanted voltage in our signal data, that is noise. So how can we create a noise? You can see, to add a noise you can create a vector from random numbers that is the same size as your signal s. So we have to use this stuff, that is, this is a function rand n which represent as a random. Okay, so task the task is create a vector of a normally distributed random numbers named noise. So the variable name is noise, noise, noise equals to rand n, that is same size as sig, multiply the vector by 0.1 to scale the vector. Okay, 0.1 into sig. Is it right or wrong? I think it is wrong. Sig into 0.1. I think it is perfect. Let's check if there is any error or not. Yes, the size input must be integer. Okay, so what we have to do, we have to cut this, and again we have to use this zero point 0.1. Let's see, it's give us the compilation error. So let's check the solution. Okay, so what we have to do, we have to multiply 0.1 before the rand signal, before the rand function, 0.1 into this, and here we have to cut it, and we need to write size. Let's check if the noise is generated or not. You can see the noise is generated here. Now what we have to do, we have to add this noise in our plot. So add the noise vector to a signal vector, name the output noise. Okay. So this is the variable we have to create. So how can we add this? We just need to write it, and then we have to signal vectors, that is sig, right, sig plus plus sig plus noise. plus noise is there, then we have to create the plot of this versus this. So basically we have to use this command again, plot t versus sig noisy. Let's check the output. Okay, poll require one of the following control system toolbox, system identification toolbox. X-axis data correctly. We have to again run this. Let's check the solution. Okay, so everything is perfect. Where it did I missed the okay. Okay, so we need to give a space, I guess. Nope. Let's give a parenthesis. Nope. It says the same. Sometimes you can get the error like this in a MATLAB. I don't know why. Okay, so I think there is something different. Okay, now you can see that this is our sig graph and this is our signal graph with the added noise. So if you want to check that which graph is nearly to the real world example, we'll always choose this one because it is not constant. This graph is constant, but this is not a constant graph. You can see here because there is a noise, and when you want to process the signal, you have to process that signal with a noise. It is very necessary. Now, signal processing toolbox contains function for common waveforms like square and sawtooth. So sawtooth is nothing but a triangular wave, but like what you can say, like a tooth or sawtooth. The input to generate a corresponding signals are similar to the inputs to the sine function. For example, this could generate the square signal. Okay, f is the frequency and t is the vector. Create a square signal. Now we have to create a square signal and we have to store that signal in a variable name sq. So we just need to copy this, and then we need to just adjust some things like this. So what is the frequency? Frequency is again 5 hertz, and then we have to create a plot which will be like this, and then just read this, and after that we have to just write here sq. Yep, and it is done perfectly. Now you can see there is another signal sq, and this is the graph for that signal. Now next thing we have to do here is try to add a noise. You can again add noise by this step. Okay, but I will not try to add noise because I already know how to
In
add
this
noise.
course, you'll perform signal processing on seismic waves from an earthquake in 2004. An earthquake shifts the rock in the Earth's crust, causing vibrations called seismic waves. The waves travel through the Earth and are picked up by a seismometer. This vibration signal is used by Earth scientists to learn about earthquake behavior.
So basically MATLAB will help you to do research. So if you want to make your career in a research, or you can say no, what is the perfect word for that? Yes, researchers, if you want to become a researchers, or you want to make your career good in research and development, and you need to learn about the matlab. Also, if you learn the matlab, you can have a big advantage in every industry, because every industry use a matlab, obviously tech related, not marketing related. But yes, matlab also has some features like finance, where the finance researchers use matlab to know the cost and the sales margin and the sales ratio and whatever the different type of stuff the finance researchers find from the matlab. Let's start.
On December 26, 2004, there was a massive earthquake in Sumatra, Indonesia. The vibrations from this earthquake traveled across the Earth's surface from Sumatra all the way to southeast Alaska, where they were picked up by 3 seismic stations. To investigate these surface waves, you'll need to do some signal processing. So let's break down the signal processing workflow. First, you'll import the signals into MATLAB. Then you'll pre-process the signals to prepare them for your analysis. After viewing the signals in the time domain, you'll look at the power spectrum in the frequency domain. You can filter your signal to keep only the frequency content that you want to focus on. As you explore your signals, you'll usually revisit earlier steps in the process to refine your algorithm. Once your signals look good, the next step depends on your application. You might want to deploy your algorithm to hardware, or you might want to extract some information from the signal.
As I said, after the signal is processed, then we have to choose that what we have to do with the processed signal. We have to use it for the actuators or device, or we have to use it just for study, like that. So this diagram is very much important, because this is a, you can say, roadmap for signal processing. So I will draw this. Import signal. After that we have to pre-process signal, then we have to analyze spectrum, then we have to filter signal again, then we have to deploy, and after that we have to calculate the features. You can say we have to study about the signals. So now the filter signal is not perfect, then we have to again go to the pre-process signal part or the analyze spectrum part. This is a
For
simple.
example, in the case of earthquakes, you could take some measurements like the timestamps of when tremors occurred. In this chapter, you'll quickly go through the signal processing workflow to learn more about the earthquake data. The rest of the course will take a deeper dive into each step.
Okay. So only 12% of course is completed. Now, what you have to do? In this module, you will process seismic signal in a signal analyzer app. Seismic station record the vertical displacement caused by a vibration in an earth crust. First, you must import the signal into workspace. The read matrix function imports a numeric matrix from a file. Okay. So what we have to do here, this is the code for the read matrix functions. Now, in this activity, you import the signal record at the HARP seismic station. The signal is stored in the file harp.csv. So import the seismic signals stored in this file to vector deb harp and plot the graph. So what we have to do, we have to do this, and we have to write this step, that is this. and we have to harp.csv. Yep. Then we have to plot the harp. Let's see if it works or not. Okay, so the data from this file is generated, and after that, that data is converted into a signal. First I have to write that. To import the signal data from files like txt or csv or etc, use function yeah. Now the next thing we have to do here is again the tutorial.
Signal Analyzer is an app for inspecting, comparing, and processing signals. To open the app, click Signal Analyzer in the Apps tab. Drag signals from the Workspace browser to the display. Since these signals are just vectors of numbers, the time information is in number of samples when you add them to the app. To change the units, select the signals and click Time Values. We already have a vector of time values in the workspace for these signals, in the vector t. To focus on one of the signals, you can clear the box next to the signal's name. Both of these signals were generated with a sine wave at 5 Hz, then 10 Hz, then 15 Hz. To view these signals in the frequency domain, go to the Display tab and click Spectrum. By default, you'll see the power spectrum of the entire signal. Or you can use the panner, then click and drag to zoom in on interesting regions, like this region with the fastest sine wave. To modify your signals, enter pre-processing mode. You'll learn more about some of these pre-processing functions later in this course. When you've finished experimenting with the app, you can export your processed signal to the MATLAB workspace or a MAT file. Or you might want to use the same steps to pre-process other signals in your application. In that case, you can generate a function with all the techniques that you chose.
Okay. So today I will complete the 40% of this course. Okay, so you can see the signal analyzer app is already open, but if you want to open in an actual MATLAB app, you have to go to the app and select the signal processing. Now what we have to do, we have to just drag the harp signal from here to the workspace browser. Sorry. Yep. Next is set the sample rate to 50. So where is the sample rate time? Let's see. I don't know how to change the sample rate. To specify the time information, select this. Yes. Time values in an analyzer tab for apps toolstrip. You can specify the start time and the sample rate fs. The start time and the time between each sample rate is this of a vector. Okay, so I have to go here, then I have to click on the sample rate and start time, and after that I have to select the sample rate, which is nothing but a 50, and click on OK, and you can see it is perfectly done. I have to click on submit, and we have to go to the next task, where the task is display the power spectrum of a harp display, harp signal. So for the spectrum part, we have to go to the display time, and then we have to go to the spectrum. Nope. To view the frequency content of the signal, you can display its power spectrum by selecting the top part of a spectrum split. Okay, the display tab of your apps tool. So like this. Okay. Now, while the app displays the power spectrum, the app's tooltips gains a spectrum tab that contains options to customize the visualization. A frequency range of these seismic surface waves is small. So to focus on a meaningful seismic activity, you can set the frequency limit to the power spectrum. So set the frequency limit from 0 Hz to 1 Hz. Set the frequency limit. So how can I set the frequency limit? Spectrum. Let's see the solution. How can I set the frequency limit here? Okay, hint. Yes, we are right at this point. We have to set this frequency limit to 0 to 1. We have to click on. Now, next step. I think the signal processing part is very. The three seismic station HARP, PAX, and WANK collect the seismic signal using different hardware. As you can see, as you have see, the data from HARP station was sampled at 50 Hz. The data from PAX station was also sampled as 50 Hz, but the hardware was imperfect. Oh. Okay. So the spacing between each sample wasn't exactly 0.02 seconds. Since the time information of a signal isn't eventually spaced, you must specify the time information at each sample. You can specify a vector instead of a sample rate by using the time values time specification. Time specifications, and this is time value, I guess. Nah, this is time limits, which is known as time values. So select the pack signal in a filter signal. So I've selected the packed signal. So where is the filter signal plane? I don't know. And select the time value. I have to choose on this. Okay. Okay, time value. And then I have to go to the time value and give the time. Select the time values on an analyzer tab and add the time information using the vector paxt. Okay. And finally display the signal. You can see signal is there. Okay, so the problem that happened here is we have to reset it. Now we have to go to this signal. I Yep, it is right. Next, set the sample rate of wank signal to 100 Hz and display the signal. The sample rate to 100 Hz. Next, display all three signals and then display the power spectrum. So we have to go to this, then we have to go to the power spectrum, then we have to go to the spectrum option, then we have to go to 0 to 1 limit option, and then we have to click on the submit. So it will run the task and our task is completed. Now we are on the next lecture.
It would be great if we always had perfect data, like when we generate a signal. But imperfect sensors normally provide imperfect data. So basically, every real-world dataset is imperfect and will need to be pre-processed before we can use it. Most signal processing techniques assume you'll have uniformly sampled signals. And if you have multiple signals, you'll also want the timestamps to match up. So how do we standardize our signals? Non-uniformly sampled signals don't have equal spacing between each point. You can interpolate the signal to new equal spacing between each point as our signals. Non-uniformly sampled signals don't have equal spacing between each point. You can interpolate the signal to new equally spaced time steps using resampling. Once all your signals are uniform, it's time to line up their timestamps. If you have multiple signals, they might be sampled at faster or slower rates, so you can change the sample rate of one signal to match another. You can upsample a signal to a faster sample rate by interpolating, or you can downsample a signal to a slower sample rate. Either way, you can't magically get new information by adding new samples to a signal. The highest frequency information you have is limited by the slowest sample rate. By downsampling, you're throwing away the high-frequency information. And by upsampling, you don't gain high-frequency information because you're just interpolating. Once the time base is cleaned up, the signal itself might also need some pre-processing. There are techniques to remove distracting patterns from a signal, like irrelevant trends and noise. We'll talk about some of these later. But first, in this lesson, you'll align the earthquake signals.
Okay, so to remove the noise from the signal, we use a sampling. And there are different types of samplings like natural sampling, ideal sampling, and there is one more which I forgot. Nyquist sampling, yes. Now, duplicate the pack signal and name a new signal as pax uniform. So how can I so I can go to this, duplicate this signal, and I will write its name as pax uniform. Use the resampling process method to resample pax uniform to 50 Hz. I'm gonna use the resampling. I just forgot it. Okay, duplicate the rename. that highlight the signal you want to process by clicking them. Yes. The next step, pre-process the highlighted signal, not the checked signal. Click the process in the analyzer tab for a tool strip to enter the process mode. In the function section of a process tab, select a processing method. Whoop. Oh, where is the processing method? Okay, so this, I think this is a, no, resample. Okay, we have to choose the resample. Okay, this is just like machine learning. Sample rate 50 hertz. Apply. How to click on apply right here. Accept all. So what is not, click the apply button. Okay, accept all, and our sampled process is processed. Okay, so I will not read this. What we have to do here, the signal record at Wrangell station has a faster sample rate of 100 hertz. Look at the full frequency range of a bank signal. Okay, so what we have to do here, we have to go to the bank, and then where the I will not click this, I will click this. So we have this. Now what we have to do, we have to go to this, display time frequency or full frequency. Let's check what the solution is. Whew. Okay, so we have to click on spectrum, and this is what we get. Is this right? Yep. Now, when you resample to a slower sample rate, frequency content above fs by 2, which is sample rate by 2, where fs is the sample rate after resampling, can distort the power spectrum. In a Wang signal, there isn't a specific power about 25 hertz, so you can try resampling the Wang signal to 50 hertz. So that is match. That it's match the sample rate of our back signal. Okay, duplicate the Wang signal. Duplicate the Wang signal. Duplicate, and then we have to slow. Wang slow. I have to right click here, and we have to duplicate it. We get a new one, we have to rename it. We have to, after renaming, then resample. For resample, we have to go to the processing, then we have to go to the resampling. After that, by a sample factor of this, where is the sample factor? This is sample factor, I guess, है ना? This is a sample factor of 0.5. Then I have to display the signal. Oh, see the signal. Is it that? No. It's 50 hertz. 0.5 sample process resampling sample factor. Where can acha, sample factor, enter the sample factor 0.5, apply, okay, accept all, and display. After displaying it, it will be perfect. No, it is not perfect. Why? Reprocessing. Well, I think I have to delete this. Yep. Again we have to duplicate, then we have to rename, then we have to reprocess, we have to use the resampling, yes, apply, okay, accept all, and now it is perfect. Now we have to click on submit. It is 50 hertz. Okay, so I didn't plot this signal. Oh, now it is getting boring, so I guess I will stop at 40% of this course. It is now at 36%. Use the panel to display the signal from about 15 minutes to 30 minutes. So I can see maximum time limits to 15 minutes to 30 minutes. No, this is not what it is. Reset. After most of the activity in a signal from our back station occurs in a small portion of each signal. You can zoom in an interesting point. Okay, the region. On the display tab, locate the region of interest selection and select the panner tool. It's a panner tool. Can you find a panner tool or not? I don't think there is a panner tool. Let's say hint. This is a panner tool which is in display option. Okay, so first we need to create the spectrum. Where's the panel tool? Inspector option, no. Here, no. Oh, this is the panel tool. Again, we have to click on reset. Yes. This is the panel option. Fifteen to 30 minutes. 15 to 30. Nope. 15 to 30. Extract the selected region from the hard packs and the actions. Whew. It's time to play some game. Extract You can extract the data from surface wave by removing extra point before and after the selected region. On the display tab in the region of interselection, select the extract signal. Extract the signals from RPAX and WAC. So these are all the signals we have. Make sure that the extract signal name this and this respectively and display them. Okay. ROI. Yes. All are perfect. We just need to display them. Why we need to crop? Oh shit. Again we have to do the reset. We need to crop this signal from 30 to 15 to 30. Okay, it will be perfect now, and then the 40% task is completed. So I guess I have to do 10% more, so it will be 50-50 for the future load. Am I right? Duplicate the hub signal and rename it as harp centimeter. Okay. So what we have to do? We have to duplicate it. Duplicate. After duplicate, we have to rename it. After renaming it, okay. Then we have to pre-process it. We have to use a custom function. Add a custom function. Name it as mn to centimeter. How can I write a name of custom function here? You can see I cannot write it. Why? I don't know. Add a custom function. Is there anything named as custom processing function? No. I can write the name of my custom function. Why? I don't know. Whew. Yeah, let's see the hint. Use the add custom function and add. But I cannot write here. I don't know why. Okay. Huh. Okay. Is this the name of the function? Yes. Apply. Okay. Accept all. Display the function. Yes. Next. Repeat the process from task 1 for person. Okay. What it said, that duplicate the two signal and append this suffix to the duplicate signal name. Select the two signal and click pre-process. After that, in pre-process mode, select the duplicated signal in a signal plane. Apply the custom function and display the signal. Okay, no problem. We have to do for this too now. Duplicate, duplicate. In here we have to write it, not delete. We have to rename it. CM CM. Okay. Now again we have to go to this, then we have to go to the pre-process, then we have to go to this, then we have to go to this function, then we have to apply, then we have to click OK, then we have to go to accept all and have to display this function. Pre-process this function, apply, OK, accept, display. Yep, no errors. Explore the three signals scale to centimeter units to the MATLAB workspace. This three signals, I don't think we have to use this. Now we need to export display this, export. Is there anything known as export? Oh shit, oh shit, we need to reset. Okay. Half centimeter, this and this also. So there are no error, and 44% task is completed. Now next thing we have to know about is Algin signals. Algin 3 signal align. Okay, Algin signal, it is not align, it is Algin. Okay, so Algin. So the seismic stations are located in different places in Alaska. So the surface wave from the earthquake in Indonesia arrived at different time. This caused a lag between the records wave. The Algin signal, also known as align signal function, Algin align two signals by delaying the earlier signal. How do you align more than two signals? Okay, so we don't have to know from this because it is the perfect place you can read and align the signal. Only two tasks we have to do from here. So let's see what we have to do. Since all three seismic stations should have a recorded the same surface wave, all three signals should be correlated. The align signal, okay, the align signal function uses a cross correlation to estimate the delay signal. To signal and film correlation. The signal with centimeter units have been renamed back to this to keep the variable name short. Align this and this. Use the variable name for output so the visualization code at the bottom of your script. Okay. So this is the task 1. Use the same variable name as this says. Align signals. I think we have to write there XY. Okay, it is perfect. Now align the packs and this. Okay. Again, I have to write that. No. Next. Okay, the 52% code is already complete. Should I learn more or not? I should say why not?
When you view a signal in the time domain, your
I will not say
investigation
why
is pretty
not.
limited.
Or should I?
For example, here are the pre-processed signals from the HARP, PAX, and Mount Wrangell seismic stations. The HARP and PAX stations look pretty similar, but the Mount Wrangell signal looks very different. Why? The Mount Wrangell signal has different frequency content from the HARP and PAX stations. All the signals have similar low frequency content, but in the Wrangell signal, it's hard to see the low frequencies with all these big spikes in the signal. Compared to HARP and PAX, the spikes contain very fast oscillations. The Wrangell signal contains high-frequency components that the other stations didn't record. Most real-world signals are composed of many frequencies. In the time domain, it's hard to see the contributions from all the frequencies. Instead, let's try viewing the signal in the frequency domain. The standard way to decompose a signal into its frequency components is to use Fourier transforms. The result is a plot where the x-axis is the frequency in hertz and the y-axis is the intensity or power of each frequency in the signal.
Oh yes, there's that.
This
I reach my limit for today. So this is all for today. We will meet in the next episode of our journey in a MATLAB. Core signal processing techniques, image processing online. Okay.